try to sell you on why that's not such a bad thing in this context. I still need to come up with a joke, an engineer wants to go to wine competition. So still working on that. But what engineers do is try to bridge the gap between science and the real world. Our whole goal is to try to take scientific theory, figure out which bits of it matter in the real world, and then what are we going to do about that now that we know how things work in the real atmosphere, in this case, is what I'm interested in. I spend most of my time thinking about air pollution in the context of it killing people and how we can make it kill fewer people, basically. What are the sources that are contributing to the most damaging parts of the atmosphere, and how can we maybe reformulate fuels or come up with control technologies for engines or whatever it is that we need to do to try to reduce that mortality. But what I'm going to try to convince you guys of today is that a lot of the techniques and the machinery that we use for that study is also very applicable to winemaking and to the damage that we've been talking about from wildfire smoke to grapes. Some of the same chemistry actually is involved in both questions. And so I'm going to try to convey some of that today, hopefully. I do want to start out though by acknowledging my co-authors. The students that worked on this were numerous, but I'll call out one here, Rashni Rajput, ran some of the simulations that I'll show today. And then Sean Refuse is not a student, he's a researcher at UC Davis in the Air Quality Research Center. And so he helped produce many of the emissions inventories that I'll talk about today. But even bigger than that, I want to acknowledge the SCRI project that Elizabeth Tomasino is the PI on, and several other people here are involved in that. And that's really what drew me into this whole discussion. And so this has been a great collaboration. I've really appreciated getting to know Aaron better, and then all of the people working on this question. I have colleagues who are atmospheric chemists who are asking me how to get involved in it. And so I think that you will find that there are many atmospheric folks who are interested in this question and want to bring their skill set to it. So, that's, I guess, you're not alone in this struggle. You've got a really tough problem that you're trying to deal with in your industry, but you're not alone in it. There's other people who want to help and can. So just to set the stage on a big picture then, these are maps that Sean produced, and then the time series on the left side. I'll see if I can get a cursor with a laser pointer to show up. Maybe not. Maybe you can see my cursor anyway. Each of these plots is an individual year, and we're looking at the total emissions of wildfires in California to the contribution that we see. And you can pick out the big years. 2020 was called out. That was a very big fire complex year, and I'll use that as a case study later on. But I do want to highlight 2017 on this map. The time series plots. It wasn't as big, but that actually had more damage for the wine sort of making in California in that year because of where and when the fires occurred. And I'll try to draw that out of the analysis. For those of you that don't know the geography of California that well, this is a plot of on the right-hand side, the central northern part of the California, where we have Napa and a lot of the other grape growing occurs. This is a plot of where those wildfires occurred, though. And so you can see it's sort of a bathtub ring around the Central Valley where most of the agriculture happens. But there was, a lot of wildfires in and around Napa, just a little bit to the northeast of San Francisco that are on the spot. And that, of course, has a really big impact as well. So I'll sort of refer back to this later on, but this sort of sets the stage. Now, why come to Washington to talk about, California wildfires? Hopefully some of the lessons that we learned in California will be translatable to you, and it'll have some useful punchlines, which is what I'm hopefully going for in this presentation. This has been introduced really well today, but we know what the compounds are that are suspected to impart the taint to the wines. They're phenolic compounds, various functional groups stuck onto them. It turns out that we've been studying this for a while, not from winemaking, but from atmospheric chemistry. These are known constituents of wildfire smoke that are very active in the atmosphere. Usually we care about these things 3 or 4 reaction steps later. We watch how these things react in the atmosphere because they're going to form condensable compounds that are going to end up in the particle phase. And in my world, what kills you fastest is particles, not the gases that are in the air. It's the particle burden. So most of you will have heard PM 2.5 as sort of an air pollution metric. That's the mass of particles with a diameter of 2.5 microns or smaller. When these phenolic compounds react, they turn into things that contribute to that PM 2.5. And so I and many other people have been worrying about them from that perspective for a long time. There's a lot known about reaction rates, how quickly they react, what they turn into. And it's, I think, translatable. The lessons are some of the tools that have been developed is translatable to your world. Now, we want to try to intersect this, though. My modeling study today is going to talk about trying to predict what's in the atmosphere from these wildfires and then intersect it with the vineyards that are in California. So this is just, again, a plot of the grape growing that is happening in California. Some of this is for table grapes, some of this is for wines. There's a wide range of things that are happening in the state. And we're looking at, going to look at the smoke impact of all of it across a long time period, actually, across a 22-year time period, all the wildfires that happened over several decades. But I'm going to try to focus in on a couple of case studies and try to take some useful lessons away from that I think are transferable. All right, so what's a chemical transport model? And I have to start with the one with all the ugly equation on it, just before I try to convince you that I'm not going to try to teach you this math. But at the essence of it, there is a competition in the atmosphere for things that are putting chemicals in the atmosphere and then things that are taking those chemicals out of the atmosphere. So if nothing reacts, then you basically just got it emitted, the wind will move it around, and then it may dry deposit to the earth or mix into the upper atmosphere. The chemistry changes that a lot, though, because you've also got chemical reactions that are transforming it into something else. And this is all happening at the same time. So it's a competition for things that are trying to increase the concentration of something and decrease the concentration of something, all happening at once. The analogy is your bank account. You have things that are trying to put things into your bank account every month and things that are taking stuff out of your bank account every month. And at the end of the month, are you up or down in your bank account? It depends on what's winning that competition. And the atmosphere is essentially the same thing. So we have these equations that describe all these processes, the rates at which they happen. They're all tied back to fundamental chemical measurements. Nothing is tuned in these chemical transport models. It's all based on running an experiment, getting a reaction rate, and then going and putting into the model, that independent measurement, then you try to predict what's happening in the atmosphere. I'm not going to sugarcoat it. This is supercomputing. I mean, we run this on big clusters. It runs for months at a time. This is not for the casual weekend sort of, I'm just going to download something and run it on my laptop. This takes data center type effort to accomplish it. But, we use it a lot for air quality and trying to understand how to make the atmosphere safe enough to breathe. And those same tools, I think you don't have to reinvent the wheel. They're available to you to take advantage of, and we can already derive lessons from it. The picture is a lot easier to understand. It's a lot more approachable just to try to convey all the complexities that are happening in the atmosphere. So there's a lot going on in this figure, but you can see in the foreground, there's a wildfire there. And then you can see somewhere in the background, there's some agricultural crops that, the wildfire is injecting things in the atmosphere, and then, that might end up impacting the crop. But everything else that's in this picture is happening at the same time as well. So it isn't just the wildfires, but you have the motor vehicle emissions, you have the, industrial emissions. Everything else is putting things in the atmosphere. There's a whole hundreds and thousands of chemical reactions that are happening in the atmosphere all at the same time. The sun is cooking it, it gets going, it is transforming into lots and lots of different things. There's interactions, with aquatic systems, land, you get deposition. There's this gas particle conversion thing where it's changing phases. Some of the products will be less volatile, and so they will end up in the particle phase rather than staying in the gas phase. That all affects what's happening. I think that the good news is the compounds that you care about are actually just at the beginning of that chain. You care about the phenolic compounds that are pretty much being directly emitted from the wildfires. So you just care in this discussion about how quickly that first thing goes away. You don't have to track it 5 stages down the road. So in some ways, your life is simplified by that. You just need to worry about the first step of the chemistry. How quickly does hydroxyl radical chew it up and make it go away in the atmosphere? So that's good news. But the bad news is that what's the concentration of hydroxyl radical? And that depends on everything else that's going on in the atmosphere at once. So you've got to do this full atmospheric simulation to really do this right. If you want to look at the decay of these things chemically in the atmosphere, you got to simulate the whole atmosphere. It's not enough to just say, I know there's wildfire smoke here, and I somehow have a decay rate. Well, was it sunny out or not sunny out? Were you near the other sources of pollution that might have encouraged the formation of hydroxyl radical or not? What season is it? All of it matters. And so you kind of have to do it all at once. So somehow simplified, but somehow not. I'm going to talk a little bit about the deposition in these models to plants because that's what we care about. We care about the phenolic compounds sort of hitting the plants and being uptaken by them. And there, again, are lots of measurements that have happened from the air pollution world to try to understand these processes. We have these models that are built. Some of them, they all have some, representation of the land surface around the place where you care about the deposition. The type of plants that are there, they vary in their degree of sophistication, but this is something that there is a truly there's an effort to represent the complexity that happens in the real world in these models. So we're going to try to take advantage of that as well. Just another quick word about the chemistry that happens here. Just to highlight again, people create smog chambers in the lab, and they put glycol in that smog chamber, and they react it with hydroxyl radical, and they watch what happens to it with 300,000 or $3 million mass spectrometers. And that is all being done for health effects research. They will take those 300,000 or $3 million mass spectrometers and put it on an airplane and fly it around a wildfire and try to figure out what's going on in the real atmosphere. There's a lot going on here. And again, that community, I think, wants to get as much bang for the buck as they can. Like by the time you put that instrument on an airplane and make measurements, you really want it to be the most useful data you can get. And so there's, I think, a willingness and an eagerness even to engage with your community to try to take the lessons that are learned in those studies and try to translate them over to winemaking. I think you would find a lot of eager people. All right, so what did we do in our study? We took the chemistry that's in these chemical transport models, and we tried to make it a little bit more specific for the phenolic compounds that we care about in this discussion. A lot of times, because there's hundreds, if not thousands of things in the atmosphere all reacting at once, that's too much complexity, and we don't really need it to describe how ozone forms or how particles form. We can simplify a little bit, but in this discussion, we really want to keep track of those phenolic compounds to make sure that we can tell you exactly how much glycol versus 4-methyl glycol versus syringol, whatever. And so we broke them out of that lumped chemistry to track individual species. Again, we know the reaction rates of a lot of these things. They've been measured in the laboratory, and we can put that into these very complicated supercomputing models, and we can track all of that through, and we can try to watch what's going to happen. So we did that with these, 4 or 5 or 6 compounds that we were tracking. We got the cresols and the glycols, syringols, and so forth. And again, I've already said this, so I won't belabor it, but you got to, put everything else that is in the atmosphere in there in a realistic way if you want to predict the oxidant field. So the oxidant, the hydroxyl radical, that is the thing that is going to react in the atmosphere with these phenolic compounds and turn them into something else, turn them into secondary organic aerosol, basically. But you don't care, again, what forms. You just care that you get rid of the phenolic compound. You're just trying to get rid of it. So we need to be able to predict that. That means that you got to put everything else that make the atmosphere as realistic as possible. So you need all the other emissions from the cars and the plants and everything else that's going on. Okay, so I'm going to focus on a case study in Central California during that 2020 wildfire complex that formed. We had this, dry lightning storm basically that started hundreds of wildfires simultaneously in Central California, including around Napa, it was just overwhelmed our ability to fight these fires. Too much was happening too fast. The plot here shows the ground level concentration of the PM 2.5. Again, the particles that are diameter smaller than 2.5 microns. You may recall, if you track these sorts of things, that you want a number, give or take 10 micrograms per cubic meter, and you're up here well above 100 in these fires. These were unhealthy events for the populations living in these areas. But of course, they also had a pretty big impact on the grapes and the wine making in the area as well. And so that's what we're going to try to untangle what's going on here. So the first thing that I want to try to, these are the big 3 or 4 slides that are going to really convey the take-home messages. Basically, all wildfires are not created equal. So the smoke composition depends on what's burning. That's been something that we've heard about today already. And if you want to look at the glycol concentration sort of relative to something else in the fire, and I picked the airborne particle concentration. We have some direct emissions of airborne particles from the wildfire, as well as gas compounds, so glycol being an example. So if that was the same everywhere, then the colors in this plot would be the same everywhere. basically you would have the same intensity color if everything was emitting glycol in the to PM at the same ratio. But it's not in these, and that's picked up in our representation of these fires. You know, we have satellite observations of the fires that we then intersect with known maps of vegetation, and there's a prediction of, you know, how much glycol. Then you can take the lab-based measurements where you're burning, you know, the shrubs versus the trees versus the whatever else, and that's all been measured, how much glycol is there versus other stuff, and that's all in this modeling framework. And so we think that this is a realistic picture, but it's, again, striking to see it sort of come up on a map that, hey, you know, if I have a fire in the coastal redwoods, that's emitting a different amount of glycol per unit of, you know, particles than if I have a shrub fire somewhere more inland or a chaparral, or, you know, it matters what's burning, how much glycol or other of these phenolic compounds are getting in the atmosphere. So you can't just look and see how bad the smoke looks. What burned to make that smoke? That is going to tell you something about how much glycol or other phenol compounds are there. So the other thing, the other big bullet point here is the stuff gets chewed up in the atmosphere. It doesn't stay constant. It's the atmospheric chemistry is going to react it. So in this plot, what I'm plotting is not the emissions, but I'm plotting the atmospheric concentrations of glycol. And I am plotting it, again, normalized by the particulate matter concentration in the atmosphere. So if it didn't react at all, the colors would stay the same here. You wouldn't see any decay as you go downwind. But in fact, what you see is that you go from dark blue to lighter blue because the glycol is reacting with hydroxyl radical. That's what theory says. We've measured that in the labs, and that's what we put in these chemical transport models. We can predict how quickly that happened. If I'm doing a good job of simulating my regional atmosphere, I know the hydroxyl radical concentration, and I can predict that decay as I go downwind. And that's what we're trying to do in these types of models. So the second big take home is that things decay, and you can tell already from this slide, it doesn't take 1,000 miles and like a month for it to happen. In the space of hours, you will start to see this decay. In the space of tens of kilometers, you will see this decay happen. And that, again, is those rates were measured in the lab with controlled experiments. We're pretty confident that's an independent sort of estimate. That's not us tuning models somehow to match what we see in the atmosphere. We need to pick this up. We need to try to measure this and look back. It's not just glycol. If I look at the other, you know, phenolic compounds that we put in the models, they're all showing that same behavior. It's the same plot now where it's the atmospheric concentration at the ground level, but at the atmospheric concentration normalized by the PM. I've scaled this obviously so that the number should come out around 1. You know, it's not a 1-to-1 glycol to PM concentration. I had to multiply by 1,000,000 or whatever, but you know, the point is that if it wasn't reacting at all, that color intensity would stay the same shade, and you can see very clearly that it's reacting away, and that I think is important. Now, the other thing that's really important to come out of this is that, you know, distance to the fire matters. Where you're seeing, this is a simulation now, not of the emissions, not of the atmospheric concentration, but the deposition. That's what you all care about, is what actually got onto the surface where the vines are. And this is a plot of where the glycol was deposited in that case study that I'm looking at. And you can see, I'll go back up, you know, a slide. You can see there was sort of a regional distribution of the stuff in the atmosphere. But if you look at where the big deposition events happen, they're close in. So it's a combination of, you know, you've got to emit it, you've got to keep it around long enough, and then it's got to be concentrated enough to deposit in any sort of considerable way to the surface. And you know, the confluence of all of that stuff, the intersection of those three considerations, you know, you can see the impacts are pretty localized. That I think is really good news for you. I know that people worry about the long-term transport of smoke, and you know, it might be coming from hundreds of miles away, but I don't think that that's really the case, at least according to these calculations. Now, again, we are just getting to the point now where we're really trying to ground truth these sorts of predictions that I'm about to show you, but you know, we're pretty confident that this is not a 1,000-mile problem. And this probably isn't even a 500-mile problem. This is a 20-mile problem that you're dealing with here. And that, I think, is an insight that translates out of California, that you can take that same message and apply it other places. just a really quick slide, what's the consequence of that? Remember the intro slide I showed, 2020 was the big fire year and 2017 was a lot smaller. But if you look at the impacts, and these are just impacts, again, I'm learning that I shouldn't just care about the post-Eurasian period. So I plotted July, August, September because I thought that that's the critical time period, but I'm getting educated at these meetings as well. And I'm learning that I need to look at a longer time window, but just focusing on that time window, then just excuse my ignorance. I'm a month or two behind the play, but 2017 was the big year for impacts in California, even though it wasn't the biggest smoke emissions year, but the smoke was in the right place and the right stuff burned to have a lot of this glycol and phenol compounds in it. And so it isn't just that you can look at a satellite image and tell whether or not there's going to be impacts to the industry. Like, what were the impacts 20 miles away? That sort of scale matters. And this shows that 2017 was the bigger impact year. Now, the winemakers in the crowd from California especially can tell me whether I'm right or wrong or not, but I think that that's what the models are predicting. Tom's not his answer, so I'm thinking so.
I think so, you're right.
So I love supercomputing. Maybe you guys can appreciate supercomputing, but you all don't have a supercomputer, I bet. You probably don't want to wait for me to pay a grad student a year to run a supercomputer, I bet. So we need to get a little bit more practical about this if we can, right? I mean, and someone told me once, sometimes you need to make something complicated before you can make it simple again. So we're trying to cross that boundary. We got to try to make it simple again. And so can we come up with a risk estimate that ironically was just the topic of conversation at lunch? Can we come up with a way to estimate the risk from a wildfire based on how far away you are, how active is the atmosphere, like how high is the oxygen concentration, some other stuff, but stuff that you can estimate or measure or get off a website at your fingertips. And so this is just a plot of the concentrations that we would predict the risk estimate essentially from the model. Trying to use just simple wind speed, distance to the fire, and ozone concentration. Those three things alone, can you predict your risk to your vineyard? And the answer is that you can kind of do okay as long as you don't try to get down to like 1 kilometer time, spatial scales. Like if you allow yourself to say, I got a 20 kilometer grid, what's my risk in that grid? Yeah, you can do it. You can't get to your neighborhood scale, but you can get to your sort of regional scale just using those simple things. And I think even what's more interesting from that is this plot, which shows how quickly those glycol concentrations are decaying away as a function of distance. And so what the grad student Rashi did in this plot was to try to look at the distribution of glycol in the atmosphere around the fire, and then how far away from the fire are we? And trying to look at like a simple decay distance. That would be even better. You don't need to know wind speed. You don't need to know ozone concentration. You just need to know how far away is the fire. And what we're seeing, at least for this fire, was that the spatial scale was around 10 kilometers, 9.1 kilometers in this plot. What that means, that it's not literally like it chops off at that. This is sort of an exponential decay thing. So by the time you go 3 of those spatial scales, you've gotten rid of 95% of your concentration. So that's the way to interpret this. By the time you get 30 kilometers away in this fire that happened in August of 2020 in around Napa, you shouldn't see much impact anymore. Inside that, it's a little dicey. So you talk about, okay, I'm safe, I'm for sure in trouble, and then there's this gray area in between where, it's call it orange, maybe would be a better color. Like maybe I've got problems, maybe I don't. And that 30 is you're fine. Right next door to you, you're definitely not fine. And then somewhere in between is where maybe you need to have a longer conversation with your chemist about what might be going on there. And that, I think, is, again, translatable. Now, we need to make sure that this is generalized. We need to study more fires. We need to get ground truth measurements. I mean, I'm confident that the curve looks like this. I'm less confident that 9.1 is the right number for everybody everywhere. And so we need to get out there and make measurements going downwind of the fire. We talked about measurement strategies, low-cost sensors getting out in places, mobile platforms. Like we literally need to chase the plumes and get measurements in the downwind gradient to verify that this is right. I know it's going to look like this. I just don't know whether 9.1 kilometers is the right number yet. And that all has to be ground truth. It is the same, models are all wrong, but some of them are useful. So that applies here. And it needs to be married to measurements. And that is when you will have All right, so the other take-home message then, again, repeating what I said before, the concentration of these compounds in vegetation changes with the vegetation type. A redwood forest is not the same as a chaparral, is not the same as other things that are going on here. The message that I leave for the folks in California is just because it hasn't burned yet doesn't mean it won't burn. So this is a picture of the different plant types, and the natural vegetation around the vineyards is known, and you can predict. It has been sort of measured and estimated what the phenolic concentration is in those plant types. And so again, just because it hasn't happened to you yet doesn't mean it can't happen. There are vulnerabilities out there. Napa's experienced some pretty severe episodes, but there are other places that could burn that would have impacts. And so we need to be just aware of that. It maybe brings up the question of, defensible space. We all have to think about defensible space in California now around your house, but maybe you need to start thinking about defensible space around your vineyard. And, what is it that is nearby that could burn? That might be something to start thinking about. There's a lot more to say about this. We've got, prescribed burning and a lot of other things that we're trying to do in California. I don't think I'm going to go into that today in the interest of time. Happy to chat about it afterwards. And I've said most of this along the way. I think, we can learn some things from the tools that we built. We think we've already got some useful information, and I don't think it's Canadian wildfires that's getting you. I think it's the wildfires next door that's probably what you need to really lose sleep over. And so hopefully that helps you focus your efforts already. And hopefully we'll come back with even more information that will be useful to you in the future. So I'll leave it at that and try to answer any questions or hold it for panel discussion afterwards.
Okay, that's a good question. We'll kind of swing into our next one because Mike will go to the airport later and won't be here for the panel discussion. So if there are any questions, let's go ahead and raise them now.
You talked about glycol and other phenols being degraded, and those degradation products being part of the secondary organic aerosol. Do we have a sense of whether any glycol or phenol or others actually make it into the secondary intact, or is it primarily degradation products?
No, it'll be the reaction products. So you start adding oxygens to these things and functional groups, and it drops the vapor pressure, and that's when they start to partition. So those things by themselves, most of them won't partition in part of the phase. So,
I'm wondering how we can adapt some of this knowledge that you've shared with topography and like wind direction off of canyons, and that would be. Yeah, so I guess the precursor to the whole supercomputing problem is we run these big net models, basically the weather research and forecasting model, trying to predict the wind direction and all those flows. That gets really hard in like canyon topographies, things where there's really extreme topography. It's hard to do that, and it's hard to pick these things out. They're regional models for the most part, and so models by themselves are never going to do it. It can't be modeled by themselves. It has to be married with local experts first off. Like, you all know where the wind goes around your vineyards. You guys know that local expertise can't be replaced. And then it needs to be married to measurements. We can't do this alone. I think the models tell a lot of useful information, and I think we drew some of that out today, but it's got to be married with other records. Question?
You highlighted the importance of deposition of these phenolic compounds as part of the risk. Are there variables that apply to the potential for deposition that provide opportunities for mitigation and prevention?
I haven't thought about that one so much, but what goes into deposition is the surface roughness, essentially. So that will affect how quickly things can sort of interact with the surface. The plant type, but I think you guys are growing vineyards, so it's hard to change the plant type. You kind of locked into the vines. So I'd have to think about that one a little bit more. I don't know whether there's any knobs to turn there or not.
I wonder even about blowers or things placed.
So that one I can't answer. That one I definitely can't answer. It turns out that the atmosphere is heavier than you think. It takes a tremendous amount of energy to move air naturally over the scales that we're talking about. So you can do some things, like people could sometimes use burners, I think, to encourage air mixing for frost damage. But for the sorts of things that we're doing to try to somehow blow the smoke plume somewhere else or ventilate it more quickly, that's a lot more air that has to get moved. And it just, the energy sort of argument doesn't work out very well. It's just, it's too much energy.
No chemical reactives that can help lower the vapor pressure.
Well, I mean, I think that I always come to these presentations and think, what could we react it with differently? To try to speed up that information, to try to do something else. But you worry about unintended consequences at that point as well. Again, the health impacts of this are non-trivial. And so we need to be really, really careful that whatever we do doesn't somehow cause a bigger public health threat. That I think I wonder about the chemistry inside the grate and what we can do there. It's, I think, a really fascinating topic, but that's where I need to find my friends who are better chemists than I. You need the chemists, not the engineers, for that conversation. But we have atmospheric chemists who are really interested.
In your modeling, have you identified, or do you know of anyone that has identified vegetation types that might have potential for like sequestration of specific compounds, or at least participate in that chemistry?
So sequestration of like we've identified vegetation types that have the higher concentrations of the phenolic compounds. So we know that if they burn, they'll emit more. But you're trying to talk about uptake of them?
Yes.
Yeah, we haven't as much. I'm not aware of anybody that's done different studies to look at how quickly different plant types will take up those phenolic compounds. But Aaron's, maybe knows more about this topic than I do. So, no.
There's something that I know we are trying to look into is it's difficult when you actually put like a hedgerow across I'm guessing that's where you're going, just maybe a hedgerow blocking your vineyard so it absorbs it versus your vines. I know some
Similar,
people
yeah.
have asked about that.
Some sort of like buffer vegetation, or just in general, just for atmospheric quality.
Even some of the research we did on prescribed burns, it didn't do too much of an impact there.
A lot of the times where I've seen discussions about vegetative barriers to air pollution, you kind of get tangled up in two things. One of them, you might get the deposition of the air pollution to the vegetation surface, but then it also changes the fluid mechanics. And so if you plant a hedgerow downwind of a freeway, you induce some mixing that might change the ground level concentrations, but you don't know what happens a mile later when that vortex kind of comes back down to the surface. So I don't think it's a super efficient way to take these compounds out of the atmosphere. It'd be a lot better to not burn them in the first place. Would be my preference.